All right. Good afternoon. Guys ready for some chemistry after this lively discussion about everything else? All right. So today we're going to dive into acid-base chemistry, kind of a bit of an overview, and then look at a couple topics we're going to dive in a little deeper into in terms of how are we approaching the more complicated acid-base problems. Of course, we've already learned some things that we could use to solve some problems, and maybe we'll take a look at kind of a couple of the basics here. I did post a homework, so you'll be able to see that. I learned that you can't submit your answers to it yet, but that'll just Moodle has some default, so unless I change that, you can't submit it until like Thursday. So I think you'll be fine. So that'll be due the day of the exam review, and we're going to go through that homework and any questions you have as exam review. And if there's something else that comes up that I realize, maybe I should have talked about a little more, I'll bring that up as well. But generally, that's kind of the plan. So today, kind of covering a little more in depth about the proton and acidity. How do we define it? What is acid-base kind of stuff, and then a little bit about how we would approach some problems. So even before we go into it, we could stop for a moment and think to ourselves, what happens if we add, let's say, a little bit of hydrochloric acid to my water, right? So presumably it's going to split apart into H plus and Cl minus, and that's a little bit simple if there's just pure water, right? We can see, as you were mentioning, Mason, like if that all dissociates into H plus and Cl minus, and that's the only thing in there, then yeah, we have some set amount of H plus. But if there's some other chemistry going on, maybe what we might call a buffer or some other base or acid present, then some other equilibrium equations get involved, and it's not just so simple as every bit of acid we add corresponds to an increase in H plus. There are other reactions happening that balance it. And so how do we do that mathematically? Well, you can imagine the more stuff that's in there, the more complicated it gets, right? So we're going to look towards how we build up what we need in order to solve that type of a problem. And when I say solve that problem, that can mean a few things. Maybe that means what is the resulting pH. Maybe that means how much acid do we need to add. There's some different types of problems we might want to solve, right? How much acid do we need to add to adjust my water bottle to pH 5, right? And whatever's in there from the tap water, probably a little bit of phosphoric acid that kind of acts as a buffer. That's our typical anti-corrosion agent. It's going to resist that a little bit. So how much do we need to add? So there's questions like that. Okay, so we're going to start with the proton, H plus. It's the first element on our table, and when it's just as the proton, with no electron, it's hanging out with a positive charge. So H plus is probably the simplest thing we can consider. Technically, there are isotopes of it, so we could have deuterium, that's an H plus or an H, but it has, we call it D because it has a neutron in addition to the proton. But we're not going to get into all that. I'm just saying mostly we're dealing with just the H plus, just a proton. So that's why you might hear things called, or hear H plus as protons or as like protic systems or protic acids or whatever. So you'll see that around. That's just referring to, on average, it's very rare to have it deuterium, so a proton with a neutron, but they exist. At any rate, pH. We talked about this already. The P is negative log of something, so pH is the negative log of our H plus concentration. Really, it's the activity, and as we talked about last time, we can find the activity, especially if there's high ionic strength. We can make some model to model what is the activity coefficient and solve for that. For the most part, we're neglecting that on purpose, knowing that we can solve it. So I think there's a problem or two on the homework where I ask you to provide the activity and solve for that. But for the large part, we're just going to say pH is the concentration with brackets, right? Ignoring the activity. Okay, so we often call pH the master variable when it comes to aquatic chemistry because it drives so many things and so many equilibrium constants are tied to it and are going to be affected by it. So if we know something about it or if we can manipulate it, chances are good we can change a lot of stuff in the chemical system. Okay, so we've got some constants. This might not be the book that you guys have, so apologize for the table numbering there, but the you can take a look at different tables, and I might have these in the next slide, so maybe I'm preempting here. But you'll have a typical table of constants at standard temperature and pressure, and these would be lookup constants for the acidity constants, we might call them, or the equilibrium constants for an acid to dissociate. So at the start I mentioned hydrochloric acid, and Mason was like, oh yeah, it's going to dissociate, right? Well, not all acids are going to do that, as we'll see today. Some of them will have an equilibrium constant where they are moderately likely to dissociate. So for example, hypochlorous acid, which is what we call bleach, HOCl, has a Ka around 10 to the negative 7.54. That means that at pH 7.5, there's equal amounts of OCl minus and HOCl, because that's going to be an equilibrium with giving off that proton, and then the result will be an OCl minus hanging out in solution. So at the pKa for a given substance, there's going to be equal amounts of the dissociated versus the still associated types. Yeah.
Will we be doing like any what am I trying to say, like the full ionization reactions where the second reactant would be water and then it would form the hydronium ion, not just like the H+?
We'll talk about it a little bit, and I don't think we'll have to worry too much about it, but it does kind of go into how these reactions work. So we'll talk about it a bit, if I understand what you're asking. Okay, so we can also note that the partitioning coefficient for water, so Kw, it's often called, will change. Actually, all of these will change with temperature, but we have lookup tables for each. We're not really going to do too much with, hey, what's the acidity if we reduce the temperature to 5 degrees Celsius or whatever. We won't do a lot of that. We already can see, based on what we've done so far with the thermodynamics, we can see how that works, right? We've done a little bit of that already. So we know that we can do that, and that's why we might have a lookup table for water. We could have a lookup table or just do the math for these other K values. But I'm just pointing out a couple things like how we approach dealing with these systems. Okay, so I have a few examples here of different acid-base reactions that we're going to be more and more familiar with, and just kind of, I've done this I think once before with you guys, just looking through some of the relevant places we're going to find acid-base chemistry. So first of all, water, of course, is an important one. Water dissociating to H plus and OH minus. Then we have the carbonate system. When CO2 dissolves and reacts with water, this is actually an equilibrium reaction as well. This is going to be, rewrite this. This is an equilibrium with this carbonic acid, H2CO3. And then that will be in equilibrium with bicarbonate, HCO3 minus and H plus. So it's acting a bit like an acid, and we'll explore that more later in the semester. And then that bicarbonate also has equilibrium with carbonate, NH plus, and this happens at a rather basic pH. So you can kind of see, depending on the pH, what amount of each carbon species we're going to have. Ammonium then is another one we'll talk about, and in this sense, the NH4 plus can dissociate, or rather it's not dissociating, it can give off an extra proton and then you have NH3 and H plus. I guess maybe you call it dissociating. But that's kind of an interesting one because it looks like it's acting like an acid, but it's also a bit of a base if you add it as NH3 because it can then take those protons and become NH4 plus. That happens because this pKa is very high. It's that reaction, that equilibrium is at a very high pH. Okay, then we have generic organic acids. So if you recall from, I think you've all taken some general organic chemistry, right? So we often talk about R, meaning like whatever else is there, whatever other part of this organic molecule. So that's R. And in this example, we're doing carboxylic groups. So the COOH, that's the carboxylic. And there's other similar functional groups that we could attach to an R, whatever R is, and have some acidity, right? So carboxylic acids are one example. But this type of thing happens a lot with random natural organic matter. Whatever happens to be in your tea, right? Whatever those molecules are, some of them will have carboxylic groups. And those have some acid-base properties. And so the large organic molecule, whatever it is, will ultimately have some acid-base chemistry there. That becomes important for things like if you want to remove it, is it going to bind and attach to some pharmaceutical that happens to be in the water or whatever else, what other chemistry you might want to consider. Okay, a few other places it's important. I feel like maybe we talked about this, or maybe we just talked about equilibrium in general. Complexation reactions, we notice that H plus can be quite important as, let's say, metals are complexing with water. So this is the source of acid mine drainage type of stuff. If you dig up a bunch of iron and it's in the Fe2 plus or Fe3 plus state, and you add water, it's going to complex with that water, and when it does so, it's releasing H plus. So this is the reason mine tailings tend to become acidic as water reaches them. So if you dig up a bunch of earth and allow these metals to oxidize with oxygen in the atmosphere, then you pour rain on it, suddenly you're going to get a lot of acidity because they wanted to complex with something. So copper does the same type of thing. Dissolution and precipitation reactions. You'll know this if you've ever done the little mineral chemistry experiment where you test to see, okay, what kind of mineral is this? One of the tests, you know, the hardness test and things, and then one, you drip a little bit of acid on it to see if it fizzes, right? So some things like calcium carbonate will dissolve and release CO2 when you add some acid to it. So if it starts fizzing and bubbling because it's dissolving and releasing CO2, we know something about that mineral. So acidity, of course, is very important to whether something is going to dissolve. And now some things dissolve really well in very basic conditions. So it's not all just whether or not there's the proton there, but certainly there's many cases where it can be important. Redox reactions, we'll talk more about later, but they often also involve, in addition to the electrons that is really the thing that makes them redox, they often also involve transfer of protons. Gas and water partitioning reactions, this is mostly the CO2. We touched on it already, but the pH of water will change how much CO2 can be in the water as dissolved gas versus as the carbonate species. And then adsorption reactions. So how likely is it for some chemical to stick to a surface? If we're trying to remove, let's say, arsenic or remove some particles with adsorption reactions, kind of calling back to those carboxylic acid groups, maybe you have a surface that has some chemistry, and then that surface, the functional groups at that surface are important. So I kind of mentioned that already. That surface can be organic or it can be inorganic. So it could be those carboxylics, or it could just be some generic hydroxyl group that's functionalized a metal or something. So whatever the case is, those surface groups can improve or reduce the affinity of some sorbate to that surface. Okay, so yeah.
Did you ever go over why the star is above the carbonic acid?
No, I'll mention it right here. basically when we write H2CO3, it's essentially saying, and we put the little star there. The star is there to note that really there's also the equilibrium of gas with dissolved, so aqueous phase CO2, and that is technically in equilibrium plus water with H2CO3. And so there's a little bit more that goes on there than just it's H2CO3, and that star is just telling us there's a little more there. So we can get into it later when we cover the carbonate system, but this involves a Henry's law constant to account for the gas exchange, and then the equilibrium constant that we'll deal with. So we can come back to that. Good question. Okay, so in general, there's lots of reasons acidity is important. Okay, so I do have at least the 3.2 table, so I'm going to recant my apology for that one at least. And we can take a look at different compilations of these K values. And what I want to draw your attention to is, so far, I've just talked about, okay, whether or not something's releasing a proton to make something acid, and then what's the result? Where is that relevant? Well, let's talk a little bit more about the types of acids we're dealing with. Because if it's just HCl, for example, this is stomach acid, by the way. It's also commonly termed muriatic acid. So if you've ever done seen it in like a household or industrial sense, hydrochloric acid, it is what we call a strong acid, like we'll see. But in small amounts, it doesn't have a hazard, like a particularly strong hazard aside from that it's an acid. Okay, so if you had a very dilute hydrochloric acid and it contacted your skin and you wash it off, you're probably going to be fine. Don't do that on purpose. But if you've ever been sick, which probably we all have, and your stomach empties forward, you'll notice you've kind of got a burning throat a little bit because there's acidity. That's hydrochloric acid, right? So one of the things you probably are going to do is brush your teeth because it's just gross. But also, one thing that'll benefit there is that there's very likely some basic and some calcium, some neutralizing things in your toothpaste, right? So doing that type of thing, part of what you're doing is trying to neutralize the acidity that is burning you. So it's not like the craziest thing, but in our stomachs, it's great because it's helping us digest things. Again, causing things to dissolve because acidic conditions can do that for a lot of substances. Okay, so HCl is pretty simple. That's going to be, when it dissociates, H plus and Cl minus. Well, some other things could release more than one proton or have more than one form of where we're at. So we might have more than one pKa. So, pKa, that's negative log of the Ka value. So a pKa of -3 means the Ka is 10 to the third. And if we recall, Ka is going to be products over reactants, meaning in the case of HCl, if the reactant is HCl and the product, if it's HCl in equilibrium with H plus and Cl minus, we are going to have this Ka means there's 1,000 times more products than the reactants. We are at equilibrium when that is true. So we are at equilibrium when there's 1,000 times more H plus in solution than there is HCl. Kind of as the way to think about it. And so it turns out that if we solved that and put it on the pH scale, the pH would have to be a negative value, -3 in fact, in order to find the equilibrium point. So we don't really consider negative pH possible in practical terms because the activity of H plus, it just kind of won't let us go there. So 0 is kind of our limit. And so if we have a negative pKa for an acid, that essentially means it's all going to dissociate. Okay, meaning there's just almost all of it is at H plus, and there's not any meaningful amount of it as HCl minus, or excuse me, HCl. Okay, so we can take a look then. Some of these, like perchloric acid, -7, so that's an extremely strong acid. And when I say extremely strong, all I mean is it's extremely likely to give up that proton. Okay, then we have some other ones that are perhaps not so strong, or maybe have a second pKa that is less strong. So sulfuric acid is a good example. The first proton it gives up, it is very happy to do so, just like hydrochloric. And the second proton it gives up, because this will be, the first proton is H2SO4. It's going to give up a proton and then have HSO4 minus. It can then give up the second proton, and it's going to do that with a pKa of about 2, meaning at pH 2, we actually have some HSO4 minus. About half of it is HSO4 minus, the other half being SO4 minus, 2 minus. And so at that point, we still call it a strong acid because I think we define it as pH 3. I have this later, so maybe I have it. Maybe it's pH 2, and I'll correct myself in a minute. But it's about 2 or 3. If it's below that, we call it a strong acid, meaning at anywhere near a normal value for water, it's strongly giving up its protons and basically dumping all of its protons into the water. And then weak acids, therefore, are something larger than that. Phosphoric acid is a good one to note here. We see that it has 3, so H3PO4. All 3 of these protons can be donated, but some of that happens at a much higher pH, right? So the first one is pretty strong. So if we have H3PO4, the first proton given up, it's kind of acting like a strong acid, but overall it's not a strong acid because then it's not giving up everything. The next one is very neutral. So we actually use it to neutralize solutions or keep them, buffer them to be pretty neutral near 7. And then the third one is given up if you go up above pH 12, right?
So does this graph, or I mean the table, does it really consider like the full ionization of these acids, and that when all of the protons are released, you mean?
It's what it's showing is when does each proton get released, in the sense of at what point are 2 species at equilibrium. I'm not sure what you mean by full ionization.
Like, is there not like 3 separate reactions where it releases one proton and then the conjugate base then releases another proton and then another?
Yeah, there are. And that's what I'm saying is each of these pKa's are that happening. So pKa 1 is the first time it happens, and pKa 2 is the second time it happens. So we can write this as some random acid with 3 protons, then pKa 1 is in equilibrium with H2A minus, and then we're going to lose another proton. I'll do this right, plus a proton. So this would be pKa 1. And then next we go and we say that H2A minus is in equilibrium with HA2 minus and a proton. That is pKa 2. And then here again we have it in equilibrium with A3 minus. This might make a little more sense when I graph it, or when we look at it graphically. But this would be pKa 3 here for that one. Yeah. Okay. Does that make some sense? All right. So my point here is that they're going to be a bit variable. We can also notice there was a question earlier about hydronium. This is another way of saying a proton, because it's water plus an extra proton. There's some debate about whether or not a proton exists by itself, or does it add itself to a water, so you have H3 instead of H2O, we have H3O plus. And so it doesn't matter too much unless you're really getting to the theory of some of this, and even then there's some debate. Okay. So how do we describe acids and bases? Well, there's a few definitions. I'm just going to go over them kind of quickly to give you a feeling for what can matter as we think about stuff acting like an acid or a base. The Arrhenius definition is pretty simple. Acids are substances that release protons in water. We can take a step further and say, okay, well, a Bronsted acid meets that and says, okay, a Bronsted acid is a proton donor, and we could say a Bronsted base is a proton acceptor. So if something can accept a proton, then we're good. So this means that a conjugate base would be the species that's formed after you release a proton. So if we go from HCl, our hydrochloric acid, and it releases our proton, Cl minus here then is our conjugate base. Because technically, that could accept a proton if we manage to force it, which normally we can't. Under normal conditions, that would have to be a negative pH. We talked about that already. But some things, let's say vinegar, you certainly can have that conjugate base receive a proton back. So conjugate acid then would be a species formed by accepting a proton. And the example would be ammonium ion when we have NH3 ammonia and a proton in equilibrium with NH4+. Okay, so then there's a slight difference if we talk about Lewis acids and Lewis bases, because these are dealing with the electron side of stuff. So a Lewis acid is an electron acceptor and a base is an electron donor. So if you think about a proton, it's kind of like, almost like the absence of an electron, because it's H+, and it might like to have an electron there. And the reason this distinction might be helpful is because some cases, like ammonia, get a little confusing if we're just looking at it as a proton. So I'm gonna read this and it'll make a little more sense. So all Bronsted acids or bases are Lewis acids or bases, but not all Lewis acids or bases are Bronsted acids or bases. So it's kind of weird that this satisfies this, or excuse me, the Lewis acid definition satisfies all Bronsted, but not necessarily vice versa. So sometimes describing it as Lewis acids or bases makes more sense. So the classic example of this is to say that for the case of ammonia, NH3 here, we have a reaction we could consider, so boron trifluoride plus ammonia, that would be in equilibrium with this combination, this molecule that's H3NBF3. So in this sense, here, I'll just read it. So here, the ammonia is a Lewis base and boron trifluoride is a Lewis acid, but there's no protons being exchanged, right? If you look at that reaction, there's no protons directly going anywhere. It's actually electrons that are happening, but it's acting as essentially a base, the ammonia is. So the Bronsted doesn't apply. It works well for a lot of things, but Lewis acid here allows it to work because it's kind of the electron transfer or donation or accepting that's really important. So don't worry too much about it. I'm just elaborating to say there are some edge cases here that we could deal with. I'm going to... I don't think that's what's to rest necessarily. No. So I think this kind of highlights why it's not always relevant, right? Whether or not there's an H+ hanging out in solution. I'm not sure if there's a definitive conclusion about whether or not there is H+. There is some discussion about it. If not in this book, then the other book. So if you're curious, I can send you some more information on that. So remind me if I don't get that to you. Yeah, it's interesting to see the debates about what all's going on there. Okay, so then another definition about acidity is do we call it strong acids or a strong base, or is it weak? And we're not really talking about strength in the normal sense. I already mentioned this, but we're basically defining it as whether or not we expect it to pretty much completely dissociate, going into its separate parts. Now this could be base or an acid. So something like NaOH is a strong base. That's going to be essentially fully dissociating to Na plus and OH minus. OH minus being the base component. That's, if we look at water, that's the conjugate base of water, right? So if we're adding a bunch of OH minus, that's kind of taking a bunch of protons, it's a proton acceptor, and therefore increasing the pH because there's fewer H pluses around. So if H plus is kind of the universal acid demarcation, then OH minus is the universal base, right? And so sometimes you'll even see problems or discussions about POH, which is just pH except inverted, right? Okay, so anyway, strong acids, strong bases, all that. So the strong ones will completely dissociate, and the conjugate bases of a strong acid are always weak bases. So that means, for example, HCl in equilibrium with H plus and Cl minus. The conjugate base, Cl minus, is a weak base, meaning, let's see, get that right. It's not going to be, if we were to do, no, the H plus would be this conjugate base. If I've got that right. Anyway, doesn't matter too much. So if we have a strong one thing, the pKa's are such that it's going to be the weak other case. And the definition for weak then is it does not fully dissociate, and the Ka is essentially greater than 3. So when I was mentioning the sulfuric acid, we call it a strong base because both pKa's are less than 3. Okay, so a weak acid then it's greater than 3. So something like vinegar, I think the pKa is 3.5 or 4-ish. A lot of it will dissociate, but not the whole thing. So acetic acid is vinegar, and some of that will go out. Okay, another table for some typical values here. We already took a look at one, so I kind of highlighted everything I think I wanted to, but there's a few more here, and this is our primary book. So that's table 7.2 if you need to go look. Okay, so here's a bit about that debate, right? The hydronium ion. So hydronium ion is H2O with an extra H, so H3O plus. Mostly it's a bit of semantics. Some say that H plus doesn't even exist, and we should instead say there's an equilibrium between H plus and H2O to get H3O plus. Now, anytime we see an equilibrium reaction like that, presumably there is some of each there. And the reason why it might not exist is because when we look at bonding in general, a solution of water is going to be comprised of all sorts of water molecules, obviously, but these are going to have sort of hydrogen bonds bridging them at random intersections. And you might have clusters that are a little more pulled together tightly, and we looked at this, I think, one of the first lectures. And so who's to say if there's an extra H plus here somewhere, is that actually connected to one of those or not? You know, this guy right here is that making an H3 plus, H3O plus, or is that just an H plus? So in that sense, is a bit of a debate. What is the real bonding going on? To some extent, who knows, who cares? But you could potentially derive the K value here. And I'm just going to read this out. So, and this is from not our main book. This is the other textbook that I drew from. So it says, so how can we, one text use H plus and another uses this H3 plus, O plus, both still come out with the same answers for a given solution? Well, neither isn't exactly correct. They both refer symbolically to all forms of H plus in solution and every possible combination of interactions with water. So since they both refer to the same quantity, as best as we can determine, we can use either one. So that, if nothing else, maybe that puts it to rest a little. Okay. Now there is one case where it becomes a little more important, or at least kind of elaborating on that little water molecule drawing that I was making. We can consider if we have H plus in equilibrium with H3O plus, and that being in equilibrium with some number of water molecules. Here's kind of the equation way to look at that, what I was drawing, right? We might have one H plus sitting around in solution, but it's kind of potentially reacting and bonding with another H2O. But so that's a question about whether or not that's reacting. But you could also just continue adding more molecules to this cluster. And we could say some number of them, right? So we could elaborate on that, go deeper into it, maybe up to 6 we could calculate. Anyway, just interesting stuff that we could maybe look at. Okay, but on to a little more practical matters. How do we solve or approach these problems? Really, it's a lot like mass balances, and we will look at mass balances. We're going to get some algebraic expression in order to find what we need. So if what we need is to find the pH, we're going to find how many unknowns we have and find enough equations so that we can solve for the unknowns, right? Anytime we've done algebra, we can have a system of equations if we have more than one unknown, right? If we have one unknown, 23 equals 4x plus 1 or something, we can solve that. There's one unknown, one equation, we solve it, right? If we have xy equals 3, now we need 2 equations because we have 2 unknowns, right? And so now that we have 2 equations here, we can solve that. So you get the point. We've done this, it's algebra. So that's overall is the approach. And this is the type of situation where we might eventually need some more computational help because we have to sometimes solve these with trial and error in certain circumstances. But we can at least set it up, and for a lot of them, we can just go ahead and directly solve. Sometimes we can graphically solve them. We'll get into that after the first exam to plot what these look like, and then it becomes kind of obvious. We say, oh, okay, these are crossing here. That must be our point of interest. So different pieces of this will come together and be more and more interesting. So we've got mass, action, expression. So there's several types of equations that we might use to build up into our system. I'll leave some notes here. Sorry to have erased them. So what we're looking for is a system of equations. So we need some number of equations for some number of unknowns. And maybe we're solving for the pH, or maybe we're solving for how much acid do we have to add to achieve some pH, right? We talked about that already. Like what's the deal? What are we aiming for? Could be different. Okay, so we can use these mass action expressions. It's a fancy way to say equilibrium constants. How is the mass acting, moving around, balancing in solution? Then we can have mass balance expressions, and we've got a couple of those to talk about. I've got a slide for each of those. Then we have charge balance equations, meaning we have to use the electroneutrality principle. We have to keep our the amount of the electrical charge, cations equal to the anions effectively. And we can also do a proton balance, which is sometimes another way to, it's related to the electroneutrality, but sometimes it's a little more convenient to work on that basis to say, okay, who's accepting and donating these protons? Sometimes we'll use what's called tote H. It's very related. It's maybe another formulation of the proton balance. And sometimes some combination, like acid neutralizing capacity. So we'll talk a bit about that. Alkalinity is a similar concept here, so we'll kind of lump that in as well. So there's several approaches we can use, several types of equations we could set up. They're going to be worth our attention, but the big picture here I want you to realize is we're essentially setting up some algebra so we can figure out the answer to a problem, okay? And then we're just drawing on the chemical principles to inform that algebra. Where are we going with it? Okay, so we'll start with the one we've already talked about, which is equilibrium constants. So already, gone into this. Just remember the p is that negative log of whatever, so we can do p of x is, going to be negative log of x. So p of, if Ka for some acid is 10 to the minus 5, then pKa is 5. You'll see this in a lot of places. You'll see it for these partitioning coefficients. Sometimes we'll see it for concentrations. We see it all over the place. So pK for water is 14 because the Kw for water, the equilibrium constant for water, is 10 to the minus 14 at a standard conditions. So we can use it for solubility, whatever. And of course, all of this is coming from the products over the reactants equation that we've talked about a few times. Okay. Need any review, any other review here? Probably not, right? Okay. So next up would be mass balance expressions. Again, this is going to be a little obvious, but hopefully we can give some nuance here. So xt would be a way to describe the total amount of x in a system, and we can simply describe that as, well, we have different species that x can occupy. The simple example we've already said was HCl and Cl minus. If x is Cl, some form of Cl, then we have the combination, the total x is a combination of HCl and Cl minus. So we're really looking at the moles, the moles of x in solution. So a little more complicated would be, and I meant to subscript this, I'm sorry, say the total phosphate. If we have H3PO4 as phosphoric acid, we would also need to account for H2PO4 minus and HPO4 2 minus and PO4 3 minus. Right? And we're talking about the molar concentrations of each of these. What you'll notice here is I'm really not caring about the protons that come off right now. I'm just looking at the number of moles of this PO4 substance, this phosphate. And that's important because that's the substance that is moving in and out of these equilibrium reactions, right? That's the constant between them, and that part isn't really changing. We might have something like acetic acid, and so I would say I'm not going to write out the entire formula of acetic acid, so I'll just leave it as AC, but it would be HAC plus AC minus, because there's one proton for acetic acid, and I can give that up. Right? So it doesn't really matter what that acid is, it just can give it up. And sometimes we'll do a generic A for acid. So HA we could look at, and A minus, right? So hopefully that is becoming more and more obvious. You could do it for a base, a generic base B. We're going to look at some formulations of that probably next time. Okay, so the point is we're just doing a mass balance on that substance, kind of ignoring whether or not a proton is attached to it or coming off of it or whatever. So that can be very helpful because that proton coming on or off does not create or destroy any of the phosphate itself, right? So we get that mass balance on the phosphate. So tote X is another way of looking at it. And this is a little more relevant in cases where we might have some other phase involved. So that's kind of typically when we use it. It's the same concept, right? The conservation of mass. But we'll say that this is where both dissolved and gas or precipitated species are affecting the mass balance. So we might say tote C would be, for total carbon, would be calcium carbonate plus carbonic acid plus bicarbonate plus carbonate. Then we might have total calcium, where we have, in a very similar system, maybe in that same exact system, we could do the separate mass balance on calcium and say, okay, well, the calcium here is in the calcium carbonate and dissolved calcium, Ca2+. Okay, so pretty straightforward, but I want to highlight that we can assemble mass balances on particular types like that where it might be helpful. Okay, next up we have the charge balance equations. And really we're talking about electroneutrality here. So the electroneutrality principle means that our net charge in any aqueous system must be 0. And so the sum of the charge equivalents of cations must be equal to the sum of the charge equivalents for the anions, right? Now we can describe that here. If M is cations in this symbol here, and that A is anions, then that would be the way to describe that mathematically, I suppose. Okay, so we can derive electroneutrality equations for a few situations. And as I mentioned, we're going to elaborate on this next time, but we could look at pure water and then stuff, right? So pure water itself is going to have H plus and OH minus in it always, because water is in equilibrium with the dissociated version, H plus and OH minus. And then we could have HA. So I already mentioned this, but HA would be considered in equilibrium with H plus and A minus. So that'd be a generic acid. We don't know if it's a strong acid or a weak acid. So, without any other information, we would say if we have pure water and HA as this generic thing, then we have all species in solution would include all the charged species would be H plus, OH minus, and A minus, right? And so then we could set up a charge balance on that. Like I said, we'll spend a little more time elaborating on that and fleshing out what each of these will look like next time. Then we might have, instead of having this generic acid added as an acid, we could add it as a conjugate base by adding it in the form of NaA. So just like we could have hydrochloric acid or sodium chloride, they're both going to add Cl minus to the system, but one of them is acidic and the other is table salt, right? So in this case, this is giving us H plus and Cl minus. In this case, we get Na plus and Cl minus. So in the for a charge balance here, it's going to be a similar consideration where, in this case, perhaps there's an equilibrium involved also. We'd have Na plus and A minus. Okay, so depending on what we're adding, in this new system, we would have all of the same charge species that we have in the generic HA, but in this time we would also have Na plus. And if you notice, we're just adding essentially less acid if we added it in the form of NaA instead of HA. Okay, last we could add H2B. Sorry, that meant to be a subscript. And I'm not going to be able to. Well, so imagine that's a subscript. Apologize about that. We'll say, I'm just going to write it here. So H2B would have an example, and we can actually consider some other scenarios. We could do HNAB, let's say, or Na2B. Any of these, it doesn't really matter too much. All we're going to say about it is that we're going to end up in this particular generic example with a B2 minus. Whatever B is, B and A here are generic. Generic substances here. All I'm saying is, in terms of the electrical neutrality, summing the charges, we could have a B that's a -1. In this case, I'm just using an example with a B of a -2. They are going to have some charge. So here we have A as a -1 and B as a -2, and maybe we could do C as -3. For example, that's kind of the thought here. It doesn't really matter too much, but we need to account for how much charge. So just letting you know, there are ways to handle this, and we're going to get more into that and derive them a little more clearly next time. Okay, next up is proton balances, and these are very similar to our electron, so electrical neutrality balances. But essentially, so we could call it that, or we could maybe call it a mass balance on the proton, perhaps. But in the sense that H plus is in equilibrium with water, and OH minus also matters here, sometimes it's helpful to just have a separate balance for protons than the electroneutrality or the mass, right? And even in the mass balance, we kind of neglected the fact that H plus was around, right? So in terms of the proton balance, we will often be making a balance sheet of H plus versus OH minus. Okay, so this is one other equation we could add to our set, and a proton balance equation, therefore, would answer the question of which species in solution have accounted for the concentration, and according to what factors. Likewise, on the other side of the equation, which species account for the OH minus in solution, and to what extent. So if we had a solution where we're adding some NaOH and some, let's say, sulfuric acid, H2SO4, and I don't know, who knows what else, maybe some calcium carbonate. We can imagine all these different ions in solution. Some of them are contributing to H plus being around. Some of them are contributing to OH minus being around. And in the case of CO3, maybe it's consuming some H plus. So it's kind of doing the opposite of contributing H plus. So there's lots of things that we can consider about where are the protons or the OH minuses going. So again, like I said, we're going to do a deeper dive next time. I'm kind of just giving the big picture today of saying, here's a few tools. We're going to use the electroneutrality, we're going to use proton balance, we're going to use mass balance, we're going to use these equilibrium constants, all these tools put together are going to give us a system of equations that we can use to solve our problems. Okay. Of course, we can add a bit to this. We could do gas exchange stuff. You know, we could do a lot of chemistry all at the same time for one big problem. But my hope is that we can take these piece by piece and understand what each one of them is doing. So next time we'll do more on mass balances and what we call alpha fractions. We'll talk more about that. And then a week from now, we'll do more on the electron neutrality and proton balances. All right. Any questions? Issues? Yeah.
It's not really a question about the material, but the slides, like they are online.
They will be. You said they're not right now?
Well, not. No, after like the certain slide, I had stopped.
Oh, I probably uploaded an old version of it maybe or something. Sorry about that. Is that for today's session?
Yeah, it's like right after the typical acidity constants, the useful tables.
Okay.
The last slide.
Okay, sorry about that.
It's all good.
I'm glad I didn't show up and that was like the file I had here because I had prepared more and I must have uploaded something before it saved or something. So these will be uploaded. I'll go do that now. Yeah. So my aim is to get you the current slides fresh, unmarked beforehand, and then upload them after. So, okay. Anything else? All right. So a little early today, but have a good day.